Okay guys, so we're going to finish topic 1 from where we left off, which was this example here, example 10. And we're going to talk about strain, and then that'll be the end of this video, and then we'll move on to topic 2. Okay, so we already know about stress, and now we're going to talk about strain, which is a property that kind of goes hand in hand with stress. Okay, so when we talk about strain, we are talking about deformation. So whenever you think of the word strain, you want to think about deformation. Okay, this can be in different forms. When we talk about deformation, we could be talking about elongation. We can be talking about compression or shortening of a member, right? We could also talk about an angle of change. We'll kind of talk about that later, so I'll put it in parentheses. Rotation. Okay, but for now, we're gonna focus on normal strain, and let me see if I define that here for you. Okay, we'll define it right here. So we're gonna talk about normal strain. We have normal stress, and we also have normal strain. So normal strain, or strain in general, we assign this Greek letter epsilon. Okay, this again is elongation, and that could also mean compression, any type of elongation or compression. So we usually find the average strain, and again, this, if you guys hear me just use the term epsilon, that's what this Greek letter is. We would define that as delta S prime minus delta S divided by delta S. And I'll define what each of these are. So delta S is my original length of a member, and delta S prime is my deformed length. Okay, so let me draw here some member. And let's say I'm pulling on this member with some force P. Okay, this is in tension, and this is axially loaded member in tension, right, because I'm pulling. So you can see here that this bar is going to elongate by some dimension. So my delta S is the original length here. And my delta S prime is how much that member has changed. Okay, so we talked about normal strain. We can also talk about shear strain. Okay, and this is when deformation changes direction. So we have some kind of change in shape. Okay, so I'm going to write that here. It's a little different than normal strain, right? So typically in civil engineering, we're dealing with really teeny tiny deformations, okay? The reason for that is when you're walking in a building and you're walking on floor beams, you don't typically want to feel the movement in those beams due to your force, due to your weight, right? So we're talking about very teeny tiny deformations that are almost not, nothing that you could actually experience or feel, especially compared to the length of those members. So we're going to assume that these deformations are infinitesimal, and that allows us to use assumptions like instead of saying sine theta, we just approximate that and say that it's theta. Instead of using cosine theta, we'll approximate that to 1. And instead of using tangent theta, we'll approximate that also to theta. Or this is if it's any, we'll use 0 here or theta as well. Okay, and this is true for very small theta values, which is okay to use for CE design, because we're not trying to get our systems to move or deform too much. Okay, and we'll kind of talk more about this in the coming example, or actually in some further examples as well. Okay, So let's go over this example 11. When force P is applied to the rigid lever arm ABC, the arm rotates counterclockwise about pin A through an angle of 0.05 degrees. Determine the normal strain developed in wire BD. So now we're looking for normal strain. So just so we know what that is, we have epsilon, okay? And to solve this problem, we kind of have to figure out what's happening to this wire BD in terms of this force P on the lever arm. Okay, so I'm going to draw some axes here. Okay, and let's say that this lever arm experiences some kind of deformation. So this is my initial pin. I can't move there. I can't translate up or down or side to side. So let's say I move that to this particular location here. Basically, this had some initial angle, and we'll call that phi. Let's call this angle alpha, and let's call this angle of rotation theta. Okay, so what we're saying here is this distance from here to here, we'll call this delta BD, LBD, so the change in length of BD, okay? And we know that it's rotating through an angle of 0.05. So we know that this theta that we've defined is 0.05 degrees, okay? And this force P is still, again, pushing down. That's what's happening here, okay? So if this is the case here, we can actually solve for this angle. We can solve for alpha by saying inverse tan of 400 over 300 is just 53.1301 degrees. So we have that angle. And if that's the case, then phi is equal to 90 minus alpha plus the 0.05, which is 36.92 degrees. And we can solve for the new length here, or sorry, the length of LAD, which is going to be the square root of this triangle, 300 squared plus 400 squared. You can see this is just a 3, 4, 5 triangle. And then we can apply the law of cosines if we want to find the new length. So this basically LB, we'll call this prime D. We'll call this length here B prime, or this position B prime, right? We want to find the new length, and we can use law of cosines because this is no longer this triangle here. Actually, I'll just highlight it. This triangle is no longer a right triangle, so we can't use Pythagorean theorem to find the new length, but we can use the law of cosines. And that's equal to, so I know this looks kind of complicated, but what I'm trying to show you is that we don't actually need to go through this process. I'm going to show you how similar this is to just assuming that that angle doesn't have an effect on that length. So I'm going to show you how we're going to get the same answer regardless. We're just plugging in now. Okay, and when we plug all of this in, we end up getting 300.3491 millimeters. And now we can find epsilon of BD as LB prime D minus LBD over LBD, and that's equal to 300.3491 minus 300 over 300, and we get 0.00116 millimeters per millimeter. And basically, this is the long way of doing this problem. Okay, we had to use the law of cosines. We couldn't just assume, or we didn't just assume that tan theta is theta or cosine theta is theta. So what I'm going to show you, I'm going to call this solution 1. And I'm going to put long way. And then now I'm going to show you solution 2, which is the engineering way, where we assume basically that this change is just equal to theta AB instead of having to put the cosines and sines in there. Okay. So here is solution 2. And this is the one that you need to know. You don't need to know how to do solution 1. Okay, you just need to understand the assumptions and the approximations and kind of get to the point where you understand that that's okay to do, okay? So this only works for small strains, which is always the case for CE problems. Okay, and basically we can find the difference in length just by saying that's equal to theta LAB, and we can say that's equal to 0.05, which is given, over 180, we're going to convert this to radians, times pi radians, and then all of this times that 400 millimeters, and we get 0.3491 millimeters, and we can directly now and we get 0.00116, the exact same answer. Okay, you can see here was our first answer, and here's our second answer. Okay, so that is it for topic 1. I believe that's the last example we had. So I'm going to end this video here, upload this up to topic 1, and then I'm going to start on topic 2 for you guys.